Good afternoon, everyone, and welcome to our IM2D webinar. This is Enrico Calzolari from the Institute of Nanoscience of the National Research Council of Italy, and I will host this live event. So before entering into the core of the presentation of our IM2D software, let me spend a couple of words about the INTERSECT project. So INTERSECT is the project under which most of the things that you are going to see today has been developed. So INTERSECT is an European project that's been funded under the Horizon 2020 program. And it's a program that put together 7 teams in 5 countries in Europe. INTERSECT brought also together so many different skills and knowledge from physics, material science, electrical engineering, and computer science, and also different expertise from academy, but also from R&D labs and industries. So different knowledge, different skill, different experiences for a unique goal that in our case is to try to realize a new solution that can help the development of new disruptive electronics. What is in particular the problem that we would like to solve? The problem is the following. So when you try to develop a new technology or new device in this case, you have to co-design at the same time both the architecture and the structure of the device from one end, but also you have to optimize the material that compose this device. And even though it's quite intuitive that there is a correlation between the quality or the characteristic of the device and the final performances or the efficiency of the device at the end. So to find out a relationship between the material and the device is quite hard task. And this is particularly difficult, especially for experiment and for labs and experimentalists. So what is the main problem? The main problem is that in order to achieve this co-design between material and device, you have to know the characteristic of the material, not in a general sense, but exactly in the configuration that this material has in the device. That means that you have to know what are the ground conditions, the working conditions. You have to know what are the main characteristics in terms of doping or defects, or if there are connections or interfaces with the rest of the circuit and the rest of the work. And so this is a complicated thing that we would like to solve, at least partially, using the capability of high advanced simulation software. So the idea is to try to put together the field of the quantum mechanical atomistic material science from one end, and the advanced device modeling from the other end, try to have something that is able to explore the material workspace, having in mind as also industries as final user of this IM2D code. How we do that? Well, as I said, so we combine material modeling based on ab initio simulation from one hand, and the device modeling based on atomistic and continuum description on the other hand. And we create this connection using a set of syntactic and semantic interoperability tools. I don't want to enter into the details of these interoperability steps because it's quite technical, but so these attains to concepts like integration, automation, standardization, data exchange, data curation. So all ingredients that we put in place to have a software that is as users friendly as possible, and can be used not only by super experts in all this field, but that can be profitably used by experts or people that work in this field. So I think that I can stop here. You will see many details on this IM2D software in the next presentation. Let me just introduce what you are gonna see in the next 40-45 minutes. So this presentation is composed of 4 sections. In the first one, that we call the challenge, Professor Luca Larcher will introduce the problem, in particular from the device point of view, from the engineering point of view, focusing especially on the point that can be of interest also for industrial use. Professor Larcher is an electrical engineer and is an expert in device simulation and device design for disruptive system. In the second part, Professor Hordehon will join Professor Larcher, and together they try to answer this problem and putting in place what are the main characteristics of the main element at the basis of our IM2D code. So Professor Hordehon is the director of the Catalan Institute of Nanoscience and Technologies, and is a worldwide expert in computer material science and in code development. In the third part, you will see a live demo of our simulation box that has been given by Dr. Matteo Bertocchi. So we will see how you can use it, what are the main features of our IM2D, so you can have at least an idea of what we can do with this code. And at the end, we will have some time for your question and for the conclusion. I think that my time is over, so I would like to ask my colleague Luca Larcher to take the mic and start his presentation. Thank you very much for your attention.
Okay, so good. Yeah, I'm Luca Larcher. I'm actually, with Applied Materials. So it's a pleasure first, right, to be here. And today, what I'm going to do is to try to basically, describe which are, let's say, the challenges, right, in terms of material properties, for, the semiconductor, technology, development. Yeah, and basically, today, what I'm going to speak about is how, let's say, how much material is important, right, for the semiconductor technology development, for the device scaling. And basically, I give you, my purpose here is to give you an industrial point of view about, how much important is the material innovation and the kind of role that, material calculations, right, in connection with the electron, device performances, how this is important, right? This is really, we think, right, a key component, right, in this, in this game. Right, so as I said, right, I'm from, Applied Material, and for those of you who are not familiar with the company, right, Applied Materials is a global leader, right, in materials engineering for the manufacturing of the, advanced semiconductor devices. Basically, right, Applied Material produce, process tools and inspection tools, and we are one of the, I would say, top 3, worldwide company, and basically, right, our tools are widely used, right, to fabricate, CMOS, right, devices, right, transistors, interconnections, we are memory devices, and we are also very active, right, in partnering and packaging, right, on the advanced chip. So in this scenario, right, we are always, right, working in support of our customer, right, providing them with, a lot of technology, right, from the, wafer, from the chip, fabrication. You can see here, right, on the left, that our technologies range from deposition to thermal treatment, metals, right, inspection, etching, and so on and so forth. And we are trying, right, to set up with our, customer, right, a collaborative framework, right, when we can, of course, exploit the technology, right, and the tool knowledge, right, in order, let's say, to drive, the technology evolution. But, among the various activities that we do in this kind of context here, I want actually to stress what we are here, right, in this central row. That is, basically, right, we strongly believe that, the materials enable scaling is key to improve, right, this PPAC-T. And for those of you who are not familiar, PPAC-T is a sort of figure of merit, right, that wants to quantify, how advanced, right, a device technology, right, and the progress the technology does, right. And the first P stands for performance, power consumption, area consumption, which means money, right, and the final, and the final T stands for time. So what is really important, right, in this game here, right, is to try to drive, materials enabling, to scale down the devices, right, and improve, right, all, these, comprehensive performances. And this actually comes typically, right, with a various combination. We have, materials innovation that can go in existing, device structure. We can have new device structures, and we can have, right, at the end also new devices, right. In the last year, the semiconductor industry, right, experienced a huge challenge, right. And basically, right, we passed from, basically, right, a planar way, to produce chips to a full 3D, way to produce chip. And this, of course, has been a very strong revolution, right? For example, right here, I want just to mention, what's going on, right, for DRAM. DRAM, right, is the most used, right, memory, right, volatile memory to be used in any chip, right, together with the CPU, with the logic. And again, right, we, strongly believe that the material engineering is key, is one essential enabling component, right, to improve, the DRAM cell, performances, power, area, right, and at the end, the cost, right, the overall, combination, the overall trade-off, right, determines the advance of the technology. And you can see here, right, that, we can achieve, right, for example, in some cases, right, an increase in the performances, a reduction of the power consumption and the area, that means cost. And this typically, right, is related to some geometrical reduction of the device, right? We can shrink it more, we can reduce the area, but at the end, right, also, and you can see on the right-hand side of this slide, this actually come with a substantial innovation in terms of, materials, right? We need materials with low, resistance, right, for the wiring, with low resistance for the contact. We need, different, high-K materials for realizing, right, the storage, capacitors of the DRAM. And this actually requires a huge investment from the top, worldwide company in R&D, right, And the idea of this IM2D box is how can we sustain that effort, right? Virtualizing it, right? Using simulation to explore, alternatives instead of going, directly to the experiments. And of course, as I was saying before, right, the electronics is going 3D. We have, DRAM, I already showed, 3D NAND, I will not show, but, the 3D NAND was the first case, right, of memory going really literally, right, 3D. And the last one, but not less important one, is that right now, logic transistor, logic FET, right, moved from FinFET, which was partially 3D, to full, right, 3D structure, which are typically, right, called, gate-all-around and nanosheet. This is, again, another huge, big revolution, right? FinFET fins, right, that you can see here on the left, become taller and higher, right? The manufacturing of these kind of devices was no longer sustainable. And so what happens is that we move here, right, from the, the vertical, taller fin to, this gate-all-around, right, nanosheets stack on top of each other. This was a huge revolution. There are hard, super tough, technical challenges, a lot of material, innovations from the channel, from the process steps, and the contaminations, right? And this, of course, is again an area that for many different standpoints, right, can open up a lot of huge opportunities, right, for modeling and for the role that model and simulation can play for accelerating, right, the development. And of course, right, so I hope that I convince you, right, that for industries, right, operating in this field, for this device technology, right, development, for this PPACT acceleration, material engineering is really at the foundation, right? And what can we do, right, then, in order, let's say, to accelerate the process here, right? Again, and this is actually the scope of this presentation. We want to show you how we use modeling and simulation, right? And what we did, right, basically is a combined effort. Already, right, within Applied Material, we have a software solution, which is called Ginestra, that can bring together, connect, the material properties to the electrical device performances, right? I will show you later, right, how this can, basically, right, speed up the design of the technology devices and also the learning. But on top of that, right, once we connect the material properties, right, to the electrical device performances, we need another piece, and this other piece is represented by what we achieve within this, European-funded project is this IM2D box, right? We need to connect the material properties needed for the electrical modeling, right, to the material compositions, right, the material stoichiometry, including, the presence of defects and stuff like that. This is really key. And I think that the combination of these two can be really, can really represent a sort of backbone, right, for the, strong acceleration, right, of devices. And here, right here on the right is actually a couple of slides, right, just cut and paste from the Applied Material playbooks. You can see here, right, how many fields, all the fields, right, the inflections where this kind of structure, right, can be applied. And yeah, in order, let's say, to go and to be a little bit more specific, right, this IM2D, workflow, for, PPACT acceleration is comprised of two, basic component, right, and basically, and we have two, main workflows, right? The first workflow I want to talk about is this material to device. This is actually, okay, once we have certain, material properties, we can actually use them, Ginestra, right, our software solution to predict the electrical, device behavior. This is for designing, right, and so we actually can link the material, to the device performances, right, going forward. So we need actually to use this as is written here, to optimize the device, right, through what we call virtual DOE, right? We can actually check enormous, a wide variety, right, of different solutions without going to experiment at the experimental level. This saves money, time, allows to accelerate and allow to be more aware of what's going on. And of course, this kind of workflows here is essential, right, to sustain the material screening. The second, piece, right, of the, of this, IM2D, role played in order, let's say, to accelerate the PPACT is comprised by the opposite workflow, right? What we call device to material. In this case, basically, right, we start from the electrical, performances of device, test vehicle, whatever, and we go backward, right, to try to, use Ginestra plus this IM2D, box to try to understand and extract, the material properties and the composition. This is really key, right, because we can, in this way, right, from this device to material, workflow, we can really accelerate the learning. So the combination of these two enabled by IM2D, so are, represents to me, right, a kind of backbone which can accelerate the design from one side and the learning from the other side. And this is essential, right, to speed up the experimental activity and the development. And in the last, let me see the screen. Oh, in the last few minutes, I want just to talk to you about what we are doing internally at Applied and how we are using this at Applied, right? For example, learning acceleration, right? This actually is what falls under this, device to material workflow, right? Basically, this is a kind of intense slide, but I want just to emphasize a few components, right? You typically have the process, then you have, and the process is done, right, to produce blanket wafers, to check, right, the process parameters, test chip, and so on and so forth. Then you have metrology tools, right? Could be optical, could be electrical, could be physical. We are in this case, right, quite interested in the electrical one, applying, right, Ginestra to the electrical output. What we can do, right, we can actually detect and extract, material properties which are relevant to produce to determine the electrical, device behavior. For example, what we call the intrinsic parameters, the permittivity, the electron affinity, the band gap, and many others, as Pablo in the next session will describe. And then, and which is very important for several applications, we can also detect, extract the atomic defects, right? The imperfections due to contaminations, due to the different processes, due to the different interfaces. This is really key, especially having technology going down to few nanometer, right? As the current state of the art. But once we have got that, through Ginestra, what we need, then we need to collect and to connect, those properties here to the material composition. And again, this is the area where this IM2D box, comes into play, This is so the combination of the two allows to process electrical data and get the composition at the end. And the composition is really key, to go back to the process people and try to optimize the process. This is actually a kind of cartoon examples, but we are working on that within Applied, showing you how we can use, this kind of software simulation, software infrastructure to speed up, the learning, and then to speed up, the development. And here, a little bit more color about that, and there is nothing new in this slide, but it's just to show you, which kind of measurements, we have. We have electrical, contact measurements, but we can have also contactless measurements. We can have also optical signal. Again, we process through Ginestra. We get, for example, the map in energy, within the band gap of, the defect concentration, and applying the IM2D box, we can actually identify, really the atomic nature of the defects. Again, this is a key information, to try to better monitor, the process, and change it accordingly, in order, let's say, to achieve better performances. And this is the first, leg of how to use IM2D box to learn faster. The second component, which is always very key, is how to use this box here, to accelerate the design. Again, what we should do here, is we have to start from the right-hand side, from the electrical, which are, let's say, the electrical performances, that we would like to have, in our devices. We can actually, once we have that, we can actually use Ginestra to try to identify which are the material properties, the combination, of different material properties and different stack, allowing to achieve that, And once we have that, we can actually understand which are, in principle, the composition of the materials, which allow, to satisfy the performances that are consistent with the electrical, results. Again, this is a very important, very powerful, way, to speed up, the development, because, through this, Ginestra plus IM2D box infrastructure, we can, for example, running in HPC, we can, and we did, we check in 24 hours, 1 million of different device combination. We found the 10 most promising solutions, and then we went to fabrication with that 10 solution instead of spending time and investigating other solutions that for some reasons are less and less promising. So that's the main idea, So basically here is where we are. And here, I just, one example, showing, what we did internally, applying this kind of concept, for example, for, high-K material stack design, exploiting this, virtual DOE, enabled by IM2W, In this case, we have just some specs, which are the typical specs for DRAM capacitor or MIM capacitors, the device stack should have a current density lower than a certain amount, and a global affecting the electric constant larger than a certain amount. We tried to consider different material for confidentiality reason. I cannot tell you too much, but we have the yellow material here named as 1, the blue one named as 2. We try to combine in order, let's say, to achieve the best result, which are exactly the composition and the stack properties, allowing to match this goal here on the top. And this is actually what we did in many cases, and how actually we can use this at the industrial level. All right, so I think my time is over. I hope that I probably, I represent well, right, which are, let's say, the challenges here. And right now, I think, right, we have to show you, right, how this IM2, I would say, box, right, can help in order, let's say, to answer some of these questions, right, and to address some of these challenges.
Good afternoon, everyone. My name is Pablo Ordejon. I'm a researcher at the Catalan Institute of Nanoscience and Nanotechnology in Barcelona, and I'm one of the people involved in building this simulation box and in the part of the calculations of the material properties.
Yeah, good, Pablo, right? And yeah, again, right, Luca Larco speaking here. Yeah, one of the points, right, I already described, right, is IM2D and these two, workflows, of course, I think, right, I don't need to repeat myself, but it's critical, to get, right, material properties, right? And the key point, right, that we have in the industry is that, oh, how can I get, right, these material properties? Because, we know that we can get from literature, it is always, right, time consuming, right? There are controversial data there, the quality of data is not correct. We can actually get the material properties from, extensive, right, characterization, but this is costly, right? I want to stress that, right? It's not for free. There is a lot of money, a lot of, work time involved. And so, right, for us, it's really, very important, right, to understand, right, okay, if I need, right, how can, basically, right, get these material properties in a different way, right? How can I, calculate the properties also from, for materials, right, that I don't know with a certain composition that I can, for example, right, speculate. And, how can, this box, right, this IM2D box help me on that, right? This is the key question, right, that I want you, Pablo, to answer.
Yeah, so that's a key issue in the project, and of course, if you know the properties of the material you want to use, that's fine. You just use it for the simulation of the device. But if you don't know the properties, then you have to figure out how to do it, and you can do it from experiment, or you can look in the literature. But the IM2D box gives you a solution for that, which is much cheaper, which is just to compute the property that you need, and for that. We use atomistic first principle calculations of the properties of materials, and we have interface Ginestra, the simulation tool for the devices, to use several open source codes which allow you to compute these properties from scratch, and then to use these properties for the material, for the device simulation. So these codes are open source. They use density functional theory, which is able to predict the properties of materials with great accuracy and with a reasonable computational cost in model computers. And in particular, in INTERSECT, we have interface AIDA with two density functional codes, which are Siesta and Quantum Espresso. But AIDA, which is the driver of our calculations, the engine of driving the calculations, it's also interfaced to other density functional theory codes like CP2K or VASP. So you can have a large variety of sources for the atomistic and material simulations. The idea is that with this kind of calculations, you have access to many properties of materials. Yeah. And most of the properties that you need in Ginestra for the device simulation. So you have access, for instance, to the atomic structure, the density of states, the band structure, the band gaps, which is essential for devices, dielectric constants, effective masses, which are all of them relatively simple amounts or simple properties. But you also have access to much more complicated and involved properties to compute, like things like thermal conductivity, or the structure of defects, the formation energy of defects, the ionization potential of defects, things like that, which are much more difficult to compute. The way that we do it in IM2D is that the user doesn't have to know how to compute these properties from first principles, which again is quite involved. Computing something like, for instance, what is the charge state of a material with a defect It's a very involved calculation because you have to do calculations first of what is the structure of the defect, and then you have to compare the energies for different charge states and as a function of the chemical potential or the Fermi level, and then you have to find these crossings between these lines, and each of these lines involves many calculations. So the way we do it with IM2D is that we provide the workflows to do that automatically, so the user doesn't have to do it. You have a catalog of possible defects, and you have to understand all these defects, and you don't have to do it by yourself, and the code will do it for you. You have workflows which compute all these properties, like the defect structure or energies, but also much more complicated properties and difficult to calculate, which are, for instance, the defect migration barriers. If a defects are not really structures which are stable and immobile, they can move and they can diffuse in the material, and they can determine, for instance, what is the response of the material or the behavior of the material to changes in the temperature. If a device has to work at very high temperatures, you cannot afford the defects to move, because then that will destroy the properties of the device. And computing this migration barrier, for instance, is also very complicated. You have many ways that the defect can move, and for each of these ways, these mechanisms, you have to compute the energy barrier for moving from one place to the other, and that involves many calculations. So the idea is that in D, what we have is already programmed with workflows all these very complex calculations in the way that the user just calls the property that he or she wants to compute, and the code will do it automatically for the person. So you see in this graph a structure of the workflow that you need to compute just a defect energy, which is very complicated, but with the IM2D tool, that's made very easy for the user. So you don't have to know all these things to go ahead and compute. Again, you can do it with the codes that we already have in IM2D, but you can do it also including codes which are already linked or plugged to AIDA, which are a few of more than the ones we have in INTERSECT, but there will be more in the future, including also codes which are not ab initio. So AIDA will be linked and will be connected to codes which allow you to do classical atom potential simulations and things which are faster than DFT if you don't really need DFT. So Luca, if you want to go to the
I think you probably already answered some of these questions. I think some of the points you touch are really important, right? For example, the first two block here of question, right, are really essential for us, right? So I guess, right, that is not so important, right, to be a DFT, expert, right? And how easy it's, right, to use it. Can you a little bit, right, spend a little bit more time, which is the interface, right, stuff like that?
Yes.
Very
so. Again, I mean, all these workflows allow you to do things much more easily than you would do if you were in your lab or in your computational setup. But you don't need to be an expert to do it. Even if you use the workflows, you have several levels of expertise programmed into the IM2D box. So you can be an expert, and in that case, the code allows you to tune or to choose many internal parameters, very technical parameters, if you know how to do it and you want to go deep into the calculations, but you don't really have to do that. You have modes of use which involve intermediate or beginner users that don't need to know anything about how the codes work and how ab initio calculations work, or even what is behind these calculations, so they don't know the technical parameters. And then the box will choose the parameters for you. It will estimate which are the right parameters, and you just have to ask for the property. So you don't have to have these deep and profound skills. Actually, you don't have to have any skill on DFT.
Okay. Yeah. This is great. I think. Yeah. Oh, go ahead, Pablo. Yeah.
No, I mean the other thing is that besides these levels of user, you have also a very friendly and easy to use graphical interface, and that makes life much easier. So you have the graphical interface to prepare the runs, to analyze the runs, and to get the analysis of the results, which will do it quite automatically for you. And again, something which is really key and important is the availability of different workflows for many types of properties. and we are working continuously on having new workflows for new properties. There is also a large community of researchers working outside the INTERSECT project with AIDA, with Siesta, with Quantum Espresso, to prepare advanced workflows for even more complicated properties of materials. And of course, these are all open source, and you can download it and use them.
Okay, that's great. And are also the defect calculations, which is typically not so easy, to calculate, included in these automatic workflows?
Which one?
I mean, are also the calculation for the properties of atomic defects, included?
Yes.
Because that is typically, a property that is not it's hard to find, in the literature, and is key for many different, electron device technologies.
Right. So this is something that the DFT community has done for a long time already, but those were very, very involved calculations. So one of these calculations would almost be a PhD thesis of a student. But right now you have the workflows to compute, for instance, the charge states of a defect and compare the energies and the stability, and in which situations a defect will be charged or not, what will be the energy for charging or trapping charges or carriers in that state, and that's a key parameter to determine the performance of the device. But again, things which are more complicated than that, like the migration energy, or what would be the diffusion of a defect as a function of temperature of the device, that's also quite automated already in IM2D.
Okay, and talking about maybe something more practical, going to the okay, which is the license scheme, because I think people who are attending this webinar, they might be interested in that.
Right. So as you have seen, the box has many components. It has some components which are the density functional theory codes, AIDA, and so on. And it also has Ginestra, and each of these has a different licensing scheme. The density functional theory codes and AIDA were developed in the academic community, so they are codes which are open source, and they are free license, so you don't have to pay for them. You can actually go to the web page and download them and use them. Ginestra is the device simulator. That's a commercial product. It's owned by Applied Materials, as you very well know, and it has a proprietary license, and you have to pay a fee for that. But the rest of the components of the box, the graphical interface and so on, have also been developed with EU money from the European Union, and that's going to be distributed with a free license too.
Okay, that's great. And when it's when we can and the user can get a trial version, a beta version of that,
Yeah. So we are just finishing the project right now. Actually, this week it's the last week of the project. So we are just wrapping up all the software and all the components, and we expect to release an official version in summer this year. So a couple of months or 3 months from now. But we already have a beta version that you can use, and it's available upon request. And we would really like to have people use it and test it and give bugs to us and the comments and how can it be improved. You have the contact email here in the slide. So if anybody is interested in using that can be used right now for early adopters. So we would be very glad if people start to use it now.
Yeah. And of course, I want just to comment that also from the Ginestra perspective, of course, the beta version is free, So we have an evaluation that is free and the people can use it. All right. Yeah. Thanks a lot. Yeah, very, very interesting. Yeah.
Okay. Thank you, Luca. So now I believe we move to the next presentation, which is Matteo Bertocchi, and he's going to give the live demo of the IM2D simulation box.
Hello to everyone. I'm Matteo Bertocchi from Applied Materials. Today, I will give you a general demonstration of one of the outcomes of the INTERSECT project, as they already said, that is the IM2D box, interoperable material to device box. So before moving to the demo, let me share with you just a slide. The scheme provides an overview of the organization and the capabilities of the interoperable material-to-device toolbox. As you can see, the infrastructure is accessed by the user through the graphical user interface that connects to the several components, from the quantum mechanical codes, Quantum Espresso and Siesta, to the automation of atomistic simulation, passing through the semantic level introduced by AIDA up to the Ginestra device simulator. To achieve this goal, we have developed a common REST API shared by all the components. IM2D is divided into a GUI and two separate hubs: the interoperable hub that manages the material modeling on the right, mainly driven by AIDA, and the device modeling hub that is represented by Ginestra on the left. Since Ginestra is a commercial software property of Applied Materials, it cannot be distributed and used under the same condition of the other components. So that's the reason why we keep them separate. In between, as I've said, there is the graphical user interface that is called the Material Property Browser. It can run as a standalone application, but it is also fully integrated into Ginestra, as I will show you later. In addition, the GUI implements also the Optimade API, you can see it in the bottom, that enable the connection and the exploration of a large set of external databases that are the ones that belong to the Optimade consortium. Now I will run the application, the IM2D toolbox. We have an About button that gives you some information and references to the project and the European fundings. Then we have the preferences, where you can set the look and feel of the GUI and also the parameters of the plugin, like the address where it is located, the database of AIDA or Symfony. In particular, in Symfony, you have also to set the user expertise, that is your level of knowledge of TFT simulation. You can identify yourself as basic, intermediate, or advanced user, and the GUI will automatically adapt to your level of expertise. Then we have also the Optimate plugin and a specific implementation for materials project, just as a test case to show that this property browser can be easily extended to connect also to other databases. We can navigate into the database, we open it, we perform a free search without putting any formula, so that we get the list of all the materials and the structure that are present into the database. As you see, to some of them, they are associated also some values, for example, for the band gap. And it means that we have already computed, for example, the band gap of zinc oxide, hafnium oxide, and aluminum oxide. We can inspect an entry of the database by double-clicking on it. It will open a new tab with the structure. You can download the structure in the CIF format. You have some information, when it has been created and by who. You have information about the cell, the simulation cell, and the parameters, band gap, effective mass, relaxed energy, and the band plot. We can also navigate the other databases, materials project, and the Optimate database. Here you have a list, for example. You can search, and again, you can open an entry of the database and get the properties you are interested in. How can we populate our database? First of all, we need to add the structure we are interested in or we want to simulate. And this can be done using the upload workflow. So we select upload from CIF file. You choose the file, for example, this one, silicon. And we start the upload. And we can monitor the status of the job from the task monitor. It's running and it has already finished, and soon it will become green. Now, if we perform again a new search on the database, we will see that as the last entry, we will have the silicon structure. Here is the silicon. Now, I will go back to the slides and show you an example of the material to device workflow. in this application, we will support device design acceleration. Imagine that you want to simulate a new material or a material for which you do not know all the required properties that are necessary for the simulation. You can use IM2D either to search the properties in the existing databases, as we have seen before, or compute them directly using the Material Modeling Hub. In this particular case, I will compute the band gap for zinc oxide and provide it to the device simulator. There, I will consider a MOSFET device and I will test several materials in a layer of the gate oxide stack, running a sort of virtual design of experiment that will allow me to select the best candidate for further studies, or to, let's say, to select 3 or 4 materials for which we want to perform a real design of experiment, saving money and time. So let's go back to the material property browser again. Imagine you want to compute the band gap for zinc oxide. I've already done it. How can you do? You can go to the list of the available workflow, select the compute band gap workflow, and it will open a pop-up window with all necessary input parameters. So we need to provide the structure, the code, we will use Quantum Espresso, and the level of precision of your simulation. This will automatically define the parameters of the DFT simulation. It is based on the AIDA protocols that provide you a set of trusted parameters which represent a trade-off between the simulation accuracy and the required computational time and resources. These parameters, moreover, will be specific to the structure and the atomic species that you are simulating, and they will be the parameters used in the simulation. Then once you have filled all the fields, you can submit the job and wait for the results. Now, imagine I want to perform the same computation, but as an expert DFT material scientist that want the control on the simulation parameter. In this case, I have to change the settings, identify me as an advanced user to Symfony. I have to restart the application to perform the change. Okay, here we are again back to our database. Now I can run the same simulation, but in this case, as you can see, the list of parameters is much longer, so that you can define the convergence threshold parameters, the energy cutoff, the list of K points, and the smearing and all the parameters that will be useful to you. And in addition, once you fill the structure field, it will enable the help button that provides you a set of suggested parameters correspond to the fast, moderate, and precise simulation that are the AIDA protocols I told you before. So now you can fill all the fields and submit your computation and monitor in the task monitor. I've already run it since it's a bit long for us, and I got the value of 1.39 EV for the band gap. Then I can use it directly into Ginestra, so into the device simulator. So let's open Ginestra. I just spent a few words on Ginestra. It's an electronic device simulation software, and what makes it unique with respect to other general purpose simulators is its focus on the description of the material point defects. So imagine I open a structure, a test. Okay, this is a typical example. It's a cylindrical transistor, and the defects are represented by the red balls. So material properties and defect properties that are available through the IM2D toolbox represent the key ingredients of the device simulation. And indeed, you can find them in the material description. For example, opening the aluminum oxide, you see that it is defined by the dielectric constant, the thermal conductivity, the effective mass for electron and holes, their mobilities, and also the band gap. So the electron affinity and the band gap. And this is the value that we will use for zinc oxide, the one that we have computed. So in our example, we will study a MOSFET structure, this one, where we will vary the second layer in the gate stack, this one. So we create a test. It can be created from a list of template tests that's available here. You can have EDVD curves, EDVG, you can have AC, DC, you can compute the capacitance, you can apply stress to the system, you can simulate resistive RAM and CB-RAM operation, phase change, and degradation of your device, and so on, reliabilities. And also you can have statistical simulation. Now, I want to perform a design of the experiment. I define the electrical parameters and the physical parameters for a simulation, which are the mechanism I introduce. For example, for electron transport, I activate the tunneling into the material. Then I define the design of experiment. I let vary, as I said, the second layer. I choose these 5 materials, and I also can let vary some geometrical parameters of the device. In this case, I modify the thickness of the layer. So the first 4, as you can see, have the label default. This means that they are already present into the Ginestra database, whereas the last one is not present into our library. So I created it from scratch, taking some parameters from the literature, and in particular the band gap. For the band gap, I chose the parameter we have computed. Then we can run the simulation and have a look at the output. So we can plot the current, the drain voltage, as function of the drain voltage, of the gate voltage, and we can also plot some figure of merits. Here I plot, for example, the drain current in the on state, the ratio of the drain current in the on state with respect to the drain current in the off state. And maybe I want to maximize this ratio, and so I can inspect the results and see that the best choice will be, in this case, aluminum oxide, whereas this is the result for zinc oxide. So as you can see, it's really useful to have access to DFT atomistic simulation. And as I told you before, IM2D, the material property browser, is fully integrated into Ginestra. It will be integrated in the next release of Ginestra. Now, just for this demonstration, I've added it to this beta version. You can see that it can be opened from here, and you have exactly the same panel as before, apart that the task monitor in the preferences are embedded directly into the Ginestra GUI. And here you can see that there is an additional library, that is the material library, that is the one of Ginestra, so that you can directly import your results from Symfony or Optimat databases into the Ginestra material library. Okay. So here we have explored one of the several application cases that show how powerful is having the possibility to drive the design of a device starting from the material properties that are available in the IM2D toolbox. And I want to stress again that in some cases, atomistic simulation represents the only way to study new materials and estimate their properties. Now I will go back to the slide to the device to material workflow. In the device to material workflow, I will provide an application to the metrology and characterization of the material properties, including the material point defects. So starting from some electrical measurements, we perform a parameter extraction on some unknown quantities of the device that either are not available in literature, neither can be easily measured or inferred by the experiment. In particular, I will show a possible way to characterize the defects starting from the experimental data. So let's open Ginestra again. This is the test. Here I have a simple MIM structure composed of germanium selenide 50-50 with a certain amount of point defects that are vacancies in this case. And I have a set of experimental measurements that have been performed on it that are EV, GV curves at different temperatures. We can find them in the test. So here are the experimental data for EV curves, and we have the same for GV curves at different temperatures. We can define a list of unknown parameters to be extracted from the experimental data that you can find here. This is the list. You can see that there is the defect thermal ionization energy, that is the distance of the defect level from the bottom of the conduction band. And you also have the band gap and some other parameters. You start from a nominal value. We get it from the germanium selenide 6040. We think it's a good starting point for our optimization. And then we define a range of variation of the parameters between a minimum and a maximum. And we run the simulation, looking for the best set that can reproduce the experimental data. We can inspect how good is our set of parameters, looking at the comparison between the experimental data that are the triangles and the simulation curves with the extracted parameters. So this for EV curves, and we have the same for the conductance. Okay. And here we have a list of the extracted parameters, starting from the nominal value to the final results. So for a band gap, we found a value of 1.44. And for the defect thermal ionization energy, it has a mean value around 0.94 and a spread of 0.17. So it's these defects are located, the electrically active defects are located close to the valence band. So in this way, we have been able to characterize the defects of the material that contribute to the transport, so the one that enter in the trapping and detrapping processes of electrons, of carriers, and we can use this data to perform additional simulation. For example, we can use this parameter in other devices that include the same material. But up to now, we do not have any knowledge of the chemical and structural characteristic of these defects, and it would be really useful to be able to distinguish among all the possibilities. Are they interstitial? Are they substitutional? Are they vacancies? Are they charge defect, neutral defects, and so on? And so to have this understanding of the material structure, we need to go down to the atomistic simulation. So I will go back to the material property browser. In particular, in the material property browser, it has already been implemented a workflow that enables the computation of the defect thermal ionization energy. That is the formation energy workflow. So the formation energy workflow is an advanced and unique workflow. It's really complicated. It requires a lot of input parameters. You start from the defective supercell, so your structure with a defect. We can open this as an example. It's a germanium selenide structure with a missing atom of selenium, so a vacancy. You define the kind of defect, it's a vacancy. You can assign to it a different charge so that it can trap 1 or 2 electrons. It can be neutral or positively charged. And then you can run your simulation obtaining the defect formation energy. By means of this workflow, you will be able to create the formation energy diagram that I will show you in the next slide. This is the slide. So we are able to represent, starting from the defect formation energy, a diagram where the formation energy of the different charge defects is function of the Fermi level. So the Fermi level can vary into the band gap of the material from the valence band to the conduction band. and the intersection between the different states represent the charge state transition. In particular, the energy at which they happen correspond to the defect thermal ionization energy. Again, the properties that we have in Ginestra. So starting from the extracted value of the thermal ionization energy, we are able to understand which are the defects that enter in the transport of the device, that determine the transport of the device. And again, we can understand, for example, studying all the possible defect vacancies of germanium or selenium, which is their nature, their structure, if they are charged or not, and we can understand what happens at the microscopic level. And this allow also to drive the process of the material deposition, because if you find, let's say that germanium vacancies are important to enhance a certain electrical behavior of your device, maybe you want to introduce more defects or you want to remove them depending on the desired output, so that you can tune your the process. So here we have explored a possible connection of the experiment with the atomistic simulation that allow to extend the knowledge of the material properties and also of its characteristics in this case of the defects. This insight can later be a feedback, for example, for the fabrication process, again demonstrating the amazing power of a loop or a flow that can connect material and device simulation. Thanks for your attention, and let's meet later at the question time. And now I think I will have to pass back the mic to Arrigo.
I've seen a few on the chat. I will read this question to everyone, and we try to answer them. So the first one is from me, Song Wang. I hope to pronounce the name correctly. And the question is, so currently I am using Quantum Espresso to do DFT calculation. DFT is preferred high-performance computer, APC, to run calculation and save our time. In the case of IM2D, also Ginestra, do we need APC to do simulation? I think that maybe Pablo can answer to that.
Yeah, I'll be happy to do that. So the part of Ginestra, which is just the device simulation, is much quicker than the usual DFT. As Luca was explaining before, you can simulate many devices in a very short time, so you don't need HPC for that. The DFT part, of course, is more expensive. The DFT codes that we have can be run in any machine. You don't need a high-performance machine, but if you want to have the results in a timely manner, then you may need HPC, especially for some properties. I mean, if you want to compute just the band gap of a material, that's very quick, and you can do it just in your laptop. If you need to compute the thermal properties as a function of temperature or the diffusion barriers of some defects, that has a considerable workload, and then you need an HPC machine. The nice thing about the simulation box and AIDA is that AIDA allows you to run things in a local machine and then dispatch your DFT jobs to an external machine, to a high-performance computing center or to a cluster in your company or whatever. So you don't need to do the calculation or the simulation of the device in a powerful machine. You can do it in your desktop, and then AIDA will dispatch the necessary jobs to other resources where you have more CPU and computational time.
In this sense, maybe I can add a comment. So also IM2D implemented specific protocol also to make your data protect and secure. So this can be really important, especially for company. So you can, in any case, you can download back your data in a secure way. And so you can keep the result protected. So I can try to read the second question that is from Sheng An Teng. And it's a thank you for the nice demonstration and introduction. I have a question. So between atomistic and device simulation, Is there any other level of modeling method available in this tool? I think that I can start answer it, and maybe Luca and Pablo can add something. So at the moment, these are the two main so device and simulation. We don't have any other specific model, but in principle, we could extend this to other codes or to other model-like. So this is an ongoing work, and so time to time we have in mind to add new functionalities and new level of modeling. About instead the level of knowledge, so as we have seen by the Matteo's presentation, we have level of knowledge instead for the depending on the capability that you have. For the time being, there are most thought for the different level of about the DFT part, but I think that this can be extended easily also for the device simulation. I don't know if Luca or Pablo would like to add something to that.
I don't know, right? If I grab maybe just one small add, right, to what you said, Enrico. I think, yeah, Ginestra was really, you know, to some extent, right, created to keep data from DFT or ab initio, right, those are molecular dynamics, and try to, yeah, interpret and perform, right, you know, device level simulation. So I don't think, I would say in the hierarchy, we need another level. But, you know, as you said correctly, maybe we can have other, I would say, workflows, right, and other also codes, right, that could be actually incorporated in IM2D, right, to provide a wider, I would say, a connectivity, right, and more tools, right, and workflows, right, to calculate the material property. But in terms of hierarchy, I don't think we need any additional one, honestly, you know, from what comes from my experience. And I don't know, Pablo, if you want to add something more.
Yeah, I could add that you don't really need to go to DFT to very detailed and careful and expensive DFT calculations to do the materials modeling. As I said before, AIDA is ready to be plugged in with other atomistic simulation tools like empirical potentials or things which are much quicker. So if you don't really need a quantum mechanical description of your electrons in the material, then you can resort to more simple and more efficient and time efficient methods. And that's very easy if you have a plugin with AIDA. And there are already some classical potentials code which are interfaced with AIDA, so that could be quite easy to implement.
The other aspect that I think that is worth to mention is that, so with IM2D, you can have access directly to a lot of materials databases. So again, if you don't really need to do new calculation, you can have access to a huge set of existing data. And this can, of course, also simplify your life. Okay, so I can try to move to the next question. This is from Rakesh Kumar. So if we get access to the trial version, that this is a beta version, yes. So should we need HPC or simply we can work in our home system or lab system? I think that this is more or less the same question that we answered before. So you can do both, essentially, and it depends on the kind of simulation that you want to do, especially from the DFT part. The next question is from Christian Neumann. It says, so does Ginestra using DFT calculation, either it combine DFT with machine learning for simulation?
No, actually, and this is why, you know, we see a lot of value in this IM2D, right, box. We don't necessarily we don't actually perform ab initio, right? You know, we don't replicate by the ab initio, but we actually take the ab initio output and use that, right, in order, let's say, to incorporate the material properties and project the electrical device behavior. Yeah, another way we can actually extract the material properties is also, right, you know, processing, you know, interpreting, right, using the simulation, the electrical data, but this is another path. but we don't do that. And Ginestra was to some extent really created to take the output from the DFT and then use that output in order, let's say, to project electrical. You know, that's the way it works. And this is why we actually, you know, joined this project and we developed this IM2D model.
So the next question is, I think, again, from Minshon Wang. And so it seems like Ginestra is a powerful simulation for field effect transistor. Does Ginestra have function for a LED?
We are doing something. It's not really, you know, we don't account for the optical part, but we do something right in relation with, for example, you know, passivation layers, you know, the best stacks, right? We can actually, for example, right, you know, describe, you know, the reduction of the quantum efficiency, right, due to the non-radiative, right, leakage component. Yeah, I don't know. I would invite a person, right, you know, who ask this question to contact us. It's not, I would say, 100%, right, in our, you know, we don't have the full functionalities for that, but we can do something. And we are ready, and we did some work internally on that.
Thank you, Luca. So I don't see any other question on the chat. So, but in any case, so if you have some other question, so please switch on the mic and ask. In any case, so as we mentioned at the beginning, so we are available to answer all your questions even after the end of this live presentation. So if you have any questions, so please contact us and we will be happy to answer your question even on remote. So if there are no more questions, I think that we can move towards the end of this live presentation, and would like to recap what we presented today. So we presented you this IM2D solution software that is conceived to have a material and device co-design for different possible the device architecture, moving from the optimization of the device, starting from the characterization of the material. This is what we call the material to device workflow, or on the other way around, so searching for the best suite of materials, starting from the characteristic, the specific characteristic of a device. So, okay, this is just a list of the main features that at present are implemented in our IM2D. There are a few from the material properties characterization from DFT. As we have seen in the Matteo's presentation, a few are quite intuitive or more simple to get, as the atomic structure, the band structure, or the band gap. Other, as we have seen, are more advanced, like the formation energy of defect, the transition state, the barrier of defect, and so on. We also have a lot of possible characteristics that can be investigated from on the device side that are not only about the structure or the type of the device, but also on the type of the characterization that you can get. So about also the reliability and the variability analysis of the optimization of and the design of the device itself. About again the IM2D, so we have show you that we have different kind of knowledge level for different, let's say, profile for possible user that allows you essentially not to take care of all the possible parameters needed to run the calculation, because this IM2D platform will decide the parameter that you don't know by itself, using a lot also of automated workflow. You can have the access also to the material databases, and you can browse and you can navigate through this IM2D program using the graphical interface. As I mentioned so far, there is also the possibility to protect your data on private firewall that is quite relevant for, especially for companies. So the official release for the IM2D will be in next summer, so summer 2022, and we are happy if you are interested in it, and you will try to use this IM2D as early adopters. In case, so please contact us at this email address. So after the end of this presentation, you will receive a link for a very short survey. So if you like, so please give us a feedback answering to very few questions about this presentation. In general, so if you are interested in what you are doing, so please follow us on our web and social channel. These are all our address and account names. I think that our time it's gone. Before closing, let me thank all my colleagues, Luca Larcher, Pablo De Haan, Matteo Bertocchi, for their presentation, but also all the other that work to make this presentation possible. And of course, thank you for your attention. Thank you for attending this webinar. And we hope to have some feedback from you and to possibly to collaborate and try to use together this IM2D platform. So thank you very much again. See you. Bye-bye.